Okay, so we are on to the second section of Newton's laws. In this one, we're going to learn about Newton's first and third law. So these two are more concept-based. Newton's second law is more equation-based, so that's why I am squishing together the first and third law. And because these are more concept-based, there's not a whole lot of equations and solving math that you're going to do for these ones. You're going to have concept questions come up on the test for you to be able to explain these. All right, so the purposes for this one, we are going to learn Newton's first law. It's very important. Learn Newton's third law. And we're going to apply each of these laws to some real life situations so you can understand what's going on. Newton's first law. This one says an object in motion will stay in motion and an object at rest will stay at rest unless you have an unbalanced force acting upon it. So this one's pretty straightforward. It's also known as the law of inertia. And inertia is basically the tendency for matter or an object to keep doing what it's doing. So if it's staying at rest, it wants to stay there. If it's moving, it stays at a constant velocity in a straight line until you have some other unbalanced force acting on it. I like to call this also the couch potato law. So if you are sitting on a couch eating chips and watching something, it's very hard to get that individual up and doing something. They want to stay at rest. Couch potato law. So another way of thinking of Newton's first law is if there's no net force or the total force is zero, you're going to have some constant velocity. And even if you have an object that's not moving, it still has a constant velocity of zero. So you should be thinking kinematics. Oh, that's V equals d over t anytime you have a net force of zero. So imagine you're driving in a car. Of course, you are not driving because you're grade 11s, but you are in a car where someone else is driving. And try and imagine 3 times when you would notice your inertia. So if you're at rest, you want to stay at rest. If you're in motion, stay in motion. Take a second, think about that. So one of the ways is when you're speeding up. Anytime you step on the gas, the car wants to move faster, but you as an individual want to stay at the same speed. So you end up going backwards into your seat. Same thing when you're slowing down. The car slows down, but your body wants to keep going in a straight line at the same velocity. So you'll go forwards. And another time is when you're turning. You want to move in a straight line. So as the car turns, you want to keep going in a straight line so you feel like you're going to go sideways. So picture a water bottle sitting on a table. Or if you have problems imagining that, here's a water bottle sitting on a table for you. We want to take a look at what kind of forces are acting on this object. So we're going to have a force of gravity going down, and we also have a upwards force caused by the table. This is what's called a normal force. I'll explain more about normal forces later, but just know there's a force upwards because of the table. These two forces are balanced. Therefore, you have no acceleration. The water bottle is sitting on the table. It's not accelerating up or down, so your forces have to be balanced. That's Newton's first law. If I remove the table, there's going to be no more normal force. There's no upwards force. So our water bottle is going to only have force of gravity acting upon it. In this case, there's an unbalanced force. There's just Fg. It's unbalanced. There's nothing else opposing that. So the water bottle is going to accelerate downwards. And if it's like this type of water bottle, it's going to make a huge noise because those ones are quite loud. And this now becomes a question like we did the last 2 units with kinematics, where you have something that's dropped or something that's falling. You have your acceleration downwards is negative 9.8 when you plug it in the equation. And we've got a projectiles question. Let's move on to Newton's third law. This one says that for every action force, there's an equal in magnitude and opposite in direction reaction force. So I'll explain what that means. Say I'm pushing the wall for some reason. If I'm pushing the wall with some force, the wall is exerting a force back on my hand with the exact same magnitude, so the same number, and in the opposite direction. So if this is the wall, I'm going to push on the wall. I'm applying a force this way. The wall is exerting a force in the opposite direction with the same magnitude, so same number, but in the opposite direction. So my hand's pointing this way, the wall is pushing this way. That's action-reaction pair. We've got two forces that are not necessarily opposing each other, but they're just one causes the other. Action causes the reaction. So these pairs of forces always act on a different object. So like I said, if I'm pushing on the wall, my force is acting on the wall's force is acting on my hand. The forces, these pairs, are acting on different objects. They aren't acting on the same object. Let's apply this to a situation. So we've got 3 examples. In each of these, we want to find what is our action-reaction pair. So we have a fish that's swimming through water. What is happening is the fish pushes the water back, and by pushing the water back, the water now pushes the fish forwards. Again, notice the fish applies a force on the water, so it's acting on the water, and then the water applies a force on the fish, so it acts on the 2 different objects, not on the same object. A runner running on the ground, the runner pushes the ground back, and the ground pushes the runner forward. That's how you run. You're using Newton's third law in order to propel yourself forward. Another case, you kick a football. So you are pushing the football with your foot, and the football pushes back on your foot. And if you don't think that that's true, try kicking a bowling ball. You're going to feel that backwards force a lot more. It's going to hurt. So this is Newton's third law. You apply a force on something, it's applying a force back on you. And they have to be equal in magnitude and opposite in direction. So here's a little bit of a tricky example. Imagine a bug hitting the windshield of a truck. I'm sure you've all experienced that at some point. We want to figure out what force pair occurs in this case. So we've got the bug hitting the windshield, and the windshield then hits the bug. When I say then, it's not like the bug's like hitting the windshield and the windshield's like back to the bug. They occur at the same time. So the bug hits the windshield and the windshield hits the bug. This occurs at the exact same time. Now in this case, it doesn't matter which one's the action or which is the reaction. They are occurring at the same time. The question is, which force is bigger? The bug hitting the windshield or the windshield hitting the bug? So if you said anything except they are the same, you would have gotten this wrong. This is the tricky part. It feels like the window at the front of the truck is going to hit the bug much, much harder because the bug's dead. And if you're in the truck, you don't feel the bugs hitting your windshield. What is killing the bug is the acceleration. And we'll get into that once we look at Newton's second law. But they experience the exact same force. So even though it seems like the bug experiences a bigger force because it's now dead, it has to do with the masses. The bigger the mass, the smaller the acceleration you have. So there is Newton's first and third law. We're going to cover Newton's second law in the next lesson. And that one's the one that implies more math. So get ready to use your math brains next time. So for this next video, we're going back to an old movie, 1994, Keanu Reeves. A movie called Speed. The whole premise with this, you've got a bomb that's attached to a bus, and the bus has to keep going a certain speed, and if it goes below a certain speed, then the bomb's going to go off. So they have to keep driving the bus at a high speed in order for them to not have the bus explode. So here's a scene. Take a look. Think about what you think is wrong with the physics. So there you go, one incredible jump. This one's pretty easy because I told you it's already not true. There's only one thing that's happening, is this jump. Yeah, so this obviously is not plausible whatsoever. And if we go back here and we take a look, you can see that the bridge that is out in the part that they're trying to jump over, it's completely flat. So there's no jump, there's no ramp, there's nothing that they have for that to be able to try and reach the other side. So as they launch here, you can see once we get here, They go for the jump, and miraculously now the bus launches at this incredible angle, and it looks like there's a few pipes or something on their way, but there's no way that it's going to bring the bus up that much. And apparently it's going so fast that gravity is just ignoring it, and it goes across at the beginning. So you can even see here the bottom of the bus is already going down, but then somehow it gets all the way across and it's just traveling sideways. So there you go, Magic Physics Bus, Magic School Bus, if any of you guys know that. Here's where you get your sense of why you'd think, oh, maybe, you know, it's going fast enough, it can travel almost sideways without some sort of ramp. But as you know from projectiles, this just doesn't work. Even if you give it just a small angle, a couple degrees, it's really hard for you to be able to get across a horizontal distance. So there you go. That's what's wrong with this one.